3/6 is factoring polynomials. We're actually going to do the whole thing. So I'm going to give you something and say factor it. But the polynomial, before what we could factor is we only were able to factor trinomials, right? Or 2 by 2, right? We only knew grouping or 2 by 2 or 3 by 1, right? So we only had certain types. So now we're going to do what we have with the synthetic and the polynomial division in order to factor longer polynomials. First thing we need to know is the remainder theorem, which we've already been talking about. If the remainder is 0, then it is a factor, right? So we know that. So if the remainder is 0, it's a factor. What else do we know? If it's a factor, what we did is we ended up graphing the thing. So we said, okay, so if it's a factor, then we took these guys here and we would say graph it. And we'd say, oh, okay, so then I'd graph it. So each one of those factors ended up being one of these x-intercepts. When it's an x-intercept, that we know that it's going to be y equals 0. Does that make sense? Right? So I know for each one of those factors that it ended up being one of the roots, right, or x-intercepts. So that's what this is saying, is that the y should equal 0. So if I know it is a factor, I know that the y should equal 0 because it ends up being an x-intercept. If it's a factor, it's an x-intercept, which means that the y equals 0. Y equals 0. That's the remainder theorem. So the remainder theorem says, if the remainder is 0, then it is a factor. If it's a factor, the y has to equal 0 because it's a root. Right? So if the remainder is 0, I know it's a factor. If it's a factor, I go back and say, wait, that means that the y has to equal 0 because it's one of the roots. So that's all interconnected. Right? From the statement, if the remainder is 0, it's a factor, then when I put in that number, I should get that the y value equals 0. Does that make sense? Okay, so it's one kind of loop. So then conversely, which means opposite basically, right? So conversely, if it's a factor, then the remainder should be 0. So if the remainder is 0, I know it's a factor. If it's a factor, the remainder should be 0. So this is a backwards and forwards statement. This develops into something called the factor theorem. The factor theorem states that if x minus p, so x whatever number, is a factor of the function, if and only if f at p equals 0, the y value equals 0, right? So the y value should be 0 because it's one of the roots, right? And we know that from the graphing of it. The y value should be 0. When it says conversely, that means backwards and forwards, or backwards as well. So IFF stands for if and only if. In math, if they write IFF in some theorem, it's not a typo. It actually means if and only if. It's a short form for if and only if. If and only if means backwards and forwards. So the theorem works backwards and forwards. So if it's a factor, right? So x minus p is a factor, then we know that when we sub in that value, we should get a 0 value for the y because it's a root, right? We got the root. If I sub in a value and I see it's 0, then I can go backwards and say, hey, but I know that must be a factor, right? So it's a backwards and forwards statement. So if this is true, if the y value is 0, then it's a factor. If it's a factor, the y value should be 0 because we know it's an x-intercept. Okay, so conversely is in mathematics, they say an if and only if statement, which means it works backwards and forwards. Okay. So that's if and only if. So again, if you ever seen a math book, it say IFF, it means it's a backwards and forwards if and only if statement. Okay. So that's the factor theorem. So the factor theorem is this full circle. I know the remainder is 0, so when I put it in, I should get a y value 0 because it ends up being one of the roots. If the y value is 0, I know it's a factor. If it's a factor, I know the y value is 0. So backwards and forwards. Okay. So using that, show that x minus 2 is a factor using the factor theorem. In other words, don't divide, right? Because I know that you can do polynomial or synthetic and go, yep, it's a factor. I don't want you doing that. I want you to use the factor theorem. So the factor theorem is the fact that the y-intercept should be 0. So I want you to use the fact that the y-intercept should be 0, or sorry, x-intercept is when y equals 0. So the factor theorem is saying that when it's an x-intercept, the y value should be 0. So not by dividing. So that means that if I do this, if I go f at, and I plug in this value, 2, right, the root is 2. If I plug that into my function, I should get a y value of 0 because it's one of the roots. Okay, because it's one of the roots, the y value should be 0. That's the factor theorem. If it's a factor, it's a root. If it's a root, the y value is 0. See how it loops? Is that okay? If it's a factor, it's a root, and if it's a root, then the y value is 0. So they went y value is 0 if it's a factor. So they skipped the middle part and said the y value has to be 0. So here, if x is 2, where the root would be, if I plug that in, 2 cubed, like that, okay, and I solve for that, that's 8 minus 12 plus 10 minus 6, 4 times 3, right? 8 minus 12 is negative 4, plus 6 is going to be 10, 6. 6 minus 6 is 0. So then, show that using the factor theorem. So what's the factor theorem saying again? The factor theorem is saying that since, okay, what did I just show? F at 2 equals 0, right? That the y value is 0. By the factor theorem, I'm just using a nice sentence, therefore, x minus 2 is a factor. I don't need the bracket. I don't know why I put the bracket. Okay, x minus 2 is a factor. Okay, so try to state the theorem that you're using. I remember in university I used to always have to state the theorem that we're using. It'd say theorem 1.12, which is the factor theorem and stuff like that. Try your best, right? Because you're saying this and then this. Don't just state this. Don't just state it's a factor, because I'm asking you to use the factor theorem. So what is the factor theorem saying? The factor theorem saying is that if the y is 0, then it is an x-intercept. If it's an x-intercept, it's a factor, right? So you're using, I want you to state this part. This part is important because of that. That's why I'm concluding what I'm concluding, because I asked you to show using factor theorem. Don't do long division and don't do synthetic, because then you're not using the factor theorem. You're stating it from the from the x-intercept, the y is 0. Therefore, the factor theorem is saying that it's a factor. Okay, so you want to use the factor theorem, which is this statement. Right? A lot of people go, can I just divide it? But you're not using the factor theorem. The factor theorem cycles back around and says that if the y is 0, that's why. Yeah?
What would be the difference if you asked us to use the remainder theorem instead? Like, would it be different?
Sorry, what would be the difference if
you asked us to use the remainder theorem instead?
Then you could show that the remainder is 0, but you would state here, so the remainder theorem, so at the bottom of the page it's saying remainder theorem, so you're skipping over there. So the remainder theorem is saying that if the remainder is 0, then it's a factor. So here you would say, since the remainder is 0, therefore it's a factor. Yes, yeah, so just your conclusion would be a little different. You would still sub it in, right? So we're skipping here. So the remainder theorem states that when I plug in the number, right, so when I plug in 2 for that factor, what I get left over is the remainder. So that remainder theorem, which develops from the factor theorem, right? So it's actually interconnected. So the remainder theorem states that when I sub in that a, so you can see here I'm subbing in the a, I put it in, then I end up getting like the a minus a, because it ends up being x minus x. So if it's 2, it'd be 2 minus 2, so that goes away. So whatever's left over must be the remainder. And then here, so if I said to use remainder theorem to show, you would say, since the remainder is 0, therefore it's a factor. So you would just conclude it slightly differently. And you'd say remainder is 0 and then conclude from there. They're very interconnected though. Like they're literally the same, right, idea. If the remainder is 0, it's a factor. This is saying if the y is 0, therefore it must have been a factor because it's an x-intercept. Yes?
Why is it a minus a?
A minus a. So let's picture x minus 2, right? So then when I plug it in, f at 2, so I'm plugging it in here, what would I get in this first factor? X minus 2, which would be 2 minus 2, and then quotient, right? Quotient.
Yeah.
Yeah, plus remainder. Yeah, makes sense, right? Because it's x minus 2, so I'll put x minus 2. So whatever you plug in there, you'd be plugging in there. Yeah, so then that theorem said, hey, wait, every time I do that, I ended up just canceling that first part out, and I have left the remainder. Right, so whatever it is, if it was x minus 3, it'd be 3 minus 3, so all gone remainder. Right? So the remainder theorem tells us almost what we kind of knew anyway, but it's an additional part. So we first concluded with the factor theorem that if the remainder is 0, then it's a factor. So this is very specific. If it's 0, it's a factor. Then they kept investigating. They went, wait, but because of this, when we plug it in, this goes away. That's the remainder. So the remainder theorem tells us something else. It tells us what the remainder is. So that's an additional fact. The 0 is very specific, right? So the remainder is something else, and we're going to use that in a little bit too. Okay, so then I asked this question. So just going backwards one more time, and then we're going to go back and forth between remainder and factor theorem. So here, is this a factor? So we check it by thinking, if I sub it in, f at negative 2, the only way I know it's a factor is if it equals 0. If it doesn't equal 0, it's not a factor. Okay, so let's plug that in. So negative 2 cubed, 3 times negative 2 squared, 5 times negative 2 plus 4, negative 8, 12 minus 10 plus 4, and I get negative 2. Okay, so then you can go, okay, that did not work out, so then since f at negative 2 does not equal 0, so the factor theorem is like, if it's not 0, that's it. That's where my theorem stops. The remainder theorem kept going and said, but wait, what else do we know? So this one's saying this. So that's by the factor theorem. So the factor theorem says only that if it's not 0, we're done. Therefore, x plus 2 is not a factor. Done. Right? So if it's not 0, I'm out. Factor theorem is very, very specific. It's only for zeros. Right? 0 works or it doesn't work. That's the factor theorem. The remainder theorem is the fact that, okay, what was left over? So when I said I tried it, if I had this number left over, they discovered that, wait, if I plug that in, it gets rid of the quotient and the divisor because I tried it. So what's left over is the remainder is negative 2. So the remainder theorem continued from the factor theorem and said, okay, if it's not 0, is this significant? Yep, that's the remainder. So that number there ends up being the remainder. That's what the remainder theorem discovered. Okay, so now we know these two lovely theorems. You're not going to have to state them from nothing. We're going to use them a lot. If I said use the factor theorem, you would say, oh, because it wasn't 0. So you would have to specifically mention because of the 0. That's why I concluded what I concluded. Right, so it's very specific with that. Any questions or...